All right. Uh, Good afternoon, ladies and gentlemen.
Good afternoon.
Great. Um, you can see on your screens the test you did for me last Wednesday. Let's just go through the questions quickly, and then we'll do what we have to do for today. So the very first one, where I asked you to, I said the conjugate base of H3PO4 is, the answer is C, H2PO4 minus. Now, because I was asking you for the conjugate base of this, what it means is that that thing itself is an acid. So the question you ask yourself is, if it loses a proton, because that's what acids do, if it loses a proton, what will it become? That's the simplest question you ask yourself to get the answer, because it's an acid. If it loses a proton, how does it become? What does it become? It becomes H2PO4 with a minus sign at the top. 2, bronzoluric acid in the reaction, in that reaction, or if you observe the reaction carefully, you will see that it is clear that water is donating a proton to ammonia. You can see that clearly, because how do you know? Because the ammonia becomes ammonium at the product site. Then the water, you're left with OH minus. It can only mean that hydrogen has left water to ammonia. So it makes water, the acid, according to Bronsted-Lowry, it's a proton donor. So A is the answer to 2. Number 3, a substance that donates a pair of electrons to form coordinate covalent bond is called, okay, we've actually not done this one, but I expected you to know because I know you were taught acid, base, and salt by Mr. Mansu. Beyond that, or aside that, I also sent you the notes. I sent you the full notes of acid, base, and salt. I mean, it's a complete note I sent you in a Word document, unless you've not, uh, uh, is it a Word document that I sent? Yeah, I think so. Unless you've not studied the note. That's the note I used to teach. That's everything. Plenty notes, plenty information I have given you. And if you had read a little bit ahead, you'd have come across Lewis' concept. Any substance that donates a pair of electrons is a base, according to Lewis. Donates. This one is donates. Okay, donates. It's a bit contradictory if you look at it, or if you compare it with Bronsted-Lowry acid. It says it's a proton donor. An acid is a proton donor. A base is a proton acceptor. Lewis says a base is a donor. Bronsted-Lowry says a base is an acceptor. Lewis says a base is a donor. But what they are donating and accepting are different. In the case of Bronsted-Lowry, it is a proton. In the case of Lewis, it is an electron pair. So those are the differences you need to take note of. But we'll look at Lewis' concepts, pretty soon. Can you hear me? Can somebody hear me?
Yes,
Yes,
sir.
sir.
Excellent. Number 4, a species which is able to accept a proton is called an acid. It's as simple as that. Number 5, for the following reaction, which of the following is a conjugate acid-base pair? So conjugate acid-base pair, you have one species at the reactant site and then another at the product site. They form the pair. There is no way you can have the two species at the reactant site forming the conjugate acid-base pair. No. So once you see something like that, that one should be ruled out immediately. So the first option A cannot be right, where the species are the two reactants. No, it is always one at the reactant site and one at the product site. If you observe this carefully, C is the answer, because I see that ammonia at the reactant site become ammonium at the product site. Ammonia at the reactant site becomes ammonium at the product site. It can only mean that ammonia is accepting a proton from H2PO4 minus, the diphosphate ion. That can only be the explanation. So that the diphosphate ion then becomes the acid. Now, at the other side, if you look at the reverse reaction, okay, where the products are now reactants, so the reaction is moving from right to left now. If you look at it that way, it is obvious that this time it is the ammonium which is donating a proton back to the hydrogen phosphate ion. Okay, this one is dihydrogen phosphate. This is hydrogen phosphate ion. That is the only way by which the ammonium at the product side, now reactant side, can now become ammonia at the product side, previously the reactant side. So it makes the hydrogen phosphate ion a base. So the dihydrogen phosphate ion at the reactant side and then the hydrogen phosphate ion at the product side constitute a conjugate acid-base pair. So it makes C the right answer. It makes C the right answer. Okay, another pair that you could have seen, which is not here, would be ammonium plus, because it is the acid from the reverse direction, slash slash what? Ammonia, yeah. Ammonium plus slash ammonia. That's another pair, but you don't have that over there. So it makes C the answer. Then 6. What is the conjugate base of HCO3 minus? Again, once you are asked to find the conjugate base of something, it means the thing that you've been given to find its conjugate base is an acid. So treat the bicarbonate ion, the HCO3 minus, as an acid. So the question you ask yourself is, as an acid, what do? They donate a proton. They donate proton. So if the bicarbonate ion donates a proton, what will be left? What will become of it? Once it donates a proton, it will be left with the carbonate ion, CO3 2 minus. So it makes C the answer. Seven, the bronstelluric acid is defined as a substance that is just a definition, that acts as a proton donor. That's the only option that makes sense among the 4. So C is the answer. And question number 8, in the following reaction, which is a bronstelluric base? So select a bronstelluric base from the reaction. If you look at the reaction carefully, water at the reactant site becomes hydrozonium ion at the product site. It can only mean that water at the reactant site has accepted a proton from the oxalate ion So water then becomes the bronzolary base because it has accepted a proton to become hydrozonium ion. It makes water the bronzolary base in that reaction. So B is the right answer for question number 8. 9. Consider the following acid-base equilibrium. HCO3 minus plus water in equilibrium with H2CO3 plus OH minus. In the reaction above, the bronzolary acids are. Here, I wanted you to select all the acids, both in the forward reaction and in the backward reaction. And you agree that water is the acid in the forward reaction. How do I know? Because it is obvious that in the forward reaction, water is donating a proton, the bicarbonate ion. That's the only way by which water will then become OH minus, because one hydrogen has left it. And that's the only way by which the bicarbonate ion will now become carbonic acid. So water is one of the acids. And in the reverse reaction, you now treat these two. If you treat these two as reactants now, the carbonic acid and then the hydroxide ion as reactants, then you look at the products that are formed. The products that are formed are water and bicarbonate. Water can only come about from hydroxide if the hydroxide accepts a proton from carbonic acid. So it means that the carbonic acid is a proton donor, an acid, according to Bronsted-Lowry. So the acids in the overall reaction, both the forward and then the backward reaction, will then be water and carbonic acid. That makes C the right answer. Now, for question number 10, I ask you to write chemical equations to show how the following species act as Bronsted-Lowry acids. And these were the species. The species I gave you were ammonia, the hydroxide ion, and then the hydrogen, the dihydrogen phosphate ion, this one. These three. Write equation to show how they act as Bronsted-Lowry acids. Those are the equations I have written by just adding water to all of them. I told you that that's the simplest way to write these equations. Just add water and then force the species to donate a proton, because you are being asked to write equations to show them act as acids. So let them donate a proton. If you were to write the equation to let them behave as bases, then in this case, let them receive the proton. I'm telling you, these things are so easy. Trust me. Once you add water, let them donate the proton to water. The other thing is to, write the products right and the charges right. And I don't see why you should be getting these things wrong. Because when ammonia donates a proton to water, water becomes hydrozonium ion. That's what you see here, H3O+. Then ammonia, you'll be left with NH2 minus. Now it has to be minus so that charges balance. You see, the -1 plus the +1 will give you 0, so that the total charge at the product side is 0. As you can see at the reactant side, there is no charge. The total charge at the reactant side is also 0. So if you write the products, the formula or the formula of the products were, the charges should come out by themselves and make the equation well balanced. In the second one, let OH minus donate the proton. Water will become hydrozonium ion. And then you'll be left with O2 minus, oxygen. That's all. Oxygen 2 minus. It's as simple as that. You realize that if you add the -2 of the oxygen to the +1 of the hydrozonium ion, the total charge that will be at the reactant, at the product side, will be -1. And that's the same total charge that will be at the reactant side, the same -1 coming from the hydroxide ion, -1 there. Water is neutral, it has no charge. Then the last one to the same thing, add water. Let this donate the proton to water. You'll be left with HPO4 2 minus. It was -1. So when one hydrogen leaves it, the negative charges will increase to -2. 10 plus a mole of hydrozonium ion. So that's what I was expecting. It's as simple as that. Now, there are other species you can add and then write the equation. For instance, by the dihydrogen phosphate, you can also decide to add hydrogen phosphates. You can add hydrogen phosphate and so on and so forth. But for me, I always tell my students that to be on the safer side, just add water to all of them. It makes things easy for you. Then the last one, I asked you to define a conjugate acid-base pairs. A lot of you had it right, so it's not a problem. There are a pair of species that differ by proton, or that differ by the gain or the loss of a hydrogen atom. Select from the following species the acid-base conjugate pairs, indicating which is the acid and which is the base. So if you watch carefully, hydrogen gas or H2/H minus is one of them, this one. Because the difference between those two species is just hydrogen. So that's one pair, where H2 is the acid, H minus is a base. Another one is H2 and OH minus, water and hydroxide ion. The difference between them is just hydrogen, where water is the acid, OH minus is the base. Another one is OH minus and O2 minus. I'm telling you, it's also another pair. OH minus slash O2 minus. The difference between them is hydrogen. If OH minus loses a proton, then you're left with O2 minus. If O2 minus accepts a proton, then you will have OH minus. So they also constitute a pair, acid-base conjugate pair. And the last one is the dihydrogen phosphate ion and the hydrogen phosphate ion, where the dihydrogen phosphate ion is the acid and the hydrogen phosphate ion is the base. It's just further you can get. Now, some of you added one, you wrote ammonia, because there's ammonia over there. I don't know where you got ammonium from. Ammonium is not part of the list, but you brought ammonium by force. Some of you wrote ammonium / ammonia only because you want to make use of the ammonia, you know. But once ammonium is not part, there's nothing you can do about that. Then those of you wrote ammonia / N3, obviously you know that is wrong. I mean this. Those of you who wrote this ammonia / N3. N3 is not one of the pairs. Can you see that? Okay, I don't know what I've just done, but the point I'm making is that, yeah, this one. This one. Those of you wrote this. This is not part, because the difference between NH3 and N3 is 3 hydrogen atoms and 2 nitrogen atoms. That's the difference between them. So it certainly cannot be an acid, conjugate acid base pair. It isn't. It's not. So that's all. Some of you did very well. Some scored everything. Some of you had 20 over 20. Some had 19 over 20. Some had 18 over 20, and so on and so forth. I think overall, it was a very impressive performance. Anybody has any question for me? Sedinam. Rejoice.
Sir.
Are you following?
Sir. Yes, please.
Do you have any question?
No.
All right. Ewoyi.
Sir, please, can you go back to question 4?
All right. Yeah. Oh. Oh. A species which is able to accept a proton is called, I said an acid. Sorry. Oh, wow. I mark you down.
Yeah.
Wow. I guess I mark everybody down.
Sir, no, you didn't mark me down.
Or I mark you right.
Yes, sir.
Oh, okay. You chose base and I mark you right, or you chose acid and I mark you right.
I chose base and you mark.
Come again.
I chose base and you mark me.
And I mark you right.
Yes, sir.
All right, that's fine. That's fine. It's a base, not an acid. A species which is able to accept a proton is called a base, not an acid. Okay. So I guess once I was trying to put the answers here, I selected the wrong one. But if you chose acid somehow and I mark you right, that's wrong. Supposed to be wrong. Any other question? Okay. So let's continue from where we stopped the last time. Hydrated cations and their acidity. I think I explained this, right? Did I explain what is meant by hydrated cations? Did you look at some examples?
Yes.
Yes.
Okay. And then we wrote some equations. So what did you say is a hydrated cation? Jasper. When do we say a cation is hydrated?
Sir. Sir, a hydrated cation is any cation coordinated or surrounded by a sheaf of water molecules.
Excellent. Excellent. And we give examples. And then we wrote this equation. I believe I explained these equations, right? That if you are given any hydrated cation, the idea basically is you can be given a hydrated cation and then you'll be asked to write equation. It's as simple. Just write an equation to show how this hydrated cation acts as bronzoluric acids. That's the question they can ask you. So I explained that, you see, in all of them, I added water, but this is one of the equations you can write. This is one equation that you can write. This one, the very first equation, equation 1, is one of the equations you can write, or the general equation, which I will show you very soon. We did that the last time. So for equation 1, I added a mole of water. Then because I'm to show that the hydrated cation is an acid, one hydrogen must leave the hydrated cation to water. Then when that happens, you see, you have 6 moles of water here. What it means is that you have water 6 times. That's what it means. So when one hydrogen leaves, that one hydrogen will come from only one of the water. So you'll be left with 5 moles of the water. You'll be left with 5 moles of the water. Then the 6 mole of the water, the 6 mole is the one that has lost the hydrogen. So that one, you'll be left with just OH. OH. And that OH is minus. So it goes to reduce the +3 on the charge, or whatever charge is on the hydrated cation, by 1. It goes to reduce the charge by 1. That's how come the charge is +2. Then that hydrogen adds to water to give you the hydrosodium ion, H3O+. So this is, you can just write this equation and you are fine, equation 1, and you are fine. But somebody can also write the general equation, okay, the overall equation. And the overall equation came about as a result of the continuous loss of hydrogen by the species that are formed until the charge disappears completely. So in the second equation, this one becomes a reactant now. You see it as a reactant. Donates the proton. Water, 5 moles of water, you now have 4 moles of water. Then the hydroxide increases to 2 because you now have 2 of them. Then the charge reduces by another 1 again. Then in the third equation, this one, which is a product, becomes a reactant now. You see, 4 moles of water now becomes 3. Hydroxide ion increases to 3 moles of them. Then this time the charge vanishes completely. Okay, then I was telling you, if you add the 3 equations, this will cancel this. This will also cancel this because they are like terms. If you consider the equilibrium sign as an equal to sign, if one crosses, you have minus over the, so if you add, it becomes 0. So this is what eventually gives the this overall equation. If you add these 3 equations, then you come up with this overall equation. Oh, what is it? This one. This is the overall equation. Okay, so I was making the point that either you write this, just add a mole of water and you are fine, or you write the overall equation. And the overall equation, if you notice carefully, the charge +3 determines the moles of water you add, because there are 3 charges, you add 3 moles of water. Now the moles of water that is formed and then the moles of hydroxide that is formed at the end, if you add them, if you add the 2 moles, it must give you the mole of water in the hydrated cation. And then the moles of the hydrosodium ion is the same as the moles of water that was added. Okay, so we went ahead and I said the general equation that can guide you write this overall equation for any hydrated cation is this one. Where is it? Yeah, this one. And I remember, yeah, then I put copper over here. Carriage was the one that even drew my attention that, oh, why is the hydrated cation M, yet at the product side I used copper, and I said it was a mistake and I corrected it to the M. I remember we did this. So you see that the charge N of the hydrated cation is that mole of water that has been added. Then the mole of the water and then the mole of the hydroxide ion, if you add them, it must give you X. That's the mole of water that coordinated or surrounded the hydrated cation. Remember that in the overall equation, there must not be any charge. That's the idea. There must not be any charge on the species that is formed. So there's no charge here. You don't see anything here. Because the two species, the hydroxide there must be a certain number of hydroxides that will take away the charge completely. And then the hydrozonium ion that is formed is N, which is the same as the moles of water that you added. So an example is what is at the top using the general format. It is copper, 4 moles of water. The charge is +2, copper 2. So you added 2 moles of water. Now, if you need to take away the 2 moles of the +2 charge, then you need 2 moles of the hydroxide. You need 2 moles of the hydroxide because each one of them is -1. Now, since water you have 4 moles of water, there has to be 2 moles of water here. Or since X is 4, let me put it that way. There has to be 2 here. So that if you add a 2 to N, 2 to 2, will give you the 4. Then plus 2 moles of hydrozonium ion. So basically, that's it. Let me give you one example to try, and then we can move on from here. I want you to write equation for, write this compound down, this hydrated cation down. Write an equation, and I'll call you to read out your equation for all of us, or to all of us. Mg into bracket H2O subscript 6, like 6 moles of water. Mg magnesium being coordinated by 6 moles of water. And then in a bigger bracket, a charge of +2. So you have 1 minute, all of you, I'll call you one after the other. You read out that equation, an equation showing that this is a bronzoluric acid. Either you go by the first equation or you go by the general equation. Any one of them, you are right. 1 minute, starts now. Steven.
No, sir. Yes, sir. Please, I didn't follow the question.
Come again.
Please, I didn't follow the question.
Oh, the question is not on the slides. I said I'm just giving you a compound.
Yeah.
Mg.
Yes, the term Mg. Yes.
Into bracket H2O subscript 6. Then everything in the bigger bracket, the charge is +2.
Thank you, sir.
All right, but Steven, next time you want to talk, raise up your hand. You can't just talk when you want to.
Yes, sir.
Dorcas, let's hear from you. Dorcas, unmute yourself and talk. Your hand is up. Yes.
Say, you said MG what? I can't see the slide.
Well, I said it's not on the slide. What I'm mentioning to you is not on the slide. It is MgH2O, like
Okay.
water. Subscript 6 moles of water.
Okay.
Then in a bigger
Thank
bracket, a charge of +2.
Okay.
Theophilus.
Say, my question. I had Mg into one bracket H2O subscript 6 into a bigger bracket that's exponent 2 plus in the aqueous stage plus 2 moles of H2O, giving you Mg into one bracket H2O subscript 4 into another bracket HOH subscript 2 plus 2 moles of H3O plus or in the aqueous stage.
All right, I hear you. I will not say you are right or wrong now. Let me hear the rest too. But I hear you loud and clear. Benoni Seke. Seke, your mic is unmuted, all right, but I can't hear anything. So check your earpiece or whatever device you are using. Nadia, how are you?
Say, I had Mg into bracket H2O. That's 6 H2O. So let me start again. Mg into bracket H2O subscript 6. All in a bigger bracket. Giving us Mg into bracket.
There is no charge.
H2O
You are not putting the charge.
subscript 4. So charge at.
Come again. You start all over. I didn't hear you well.
I said Mg into bracket H2O subscript 6. All into one big bracket, charge 2 plus 2 moles of H2O. Then it will give us magnesium into bracket H2O subscript 4 into bracket OH subscript 2. That's an aqueous solution plus 2 moles of H3O plus aqueous.
All right. I hear you loud and clear. Let me hear the rest. A couple more, maybe some 2 more. Jason Awaga Chromil. Jason, talk. All right, Jason, it looks like you also have a problem with your mic. Your mic is unmuted, but I can't hear your. I could rather hear some sound at the background there. I can't hear your voice. Tenuka Rage.
Say, what about subscript 6 all to the 2 plus, giving us MgH2O subscript 4, then into bracket OH subscript 2 plus 2H plus, all in the aqueous state.
2H plus.
So what about that? I'm just asking.
You are just asking. I didn't even, so you didn't add water to no, that's wrong. All right, so what you had it right.
No.
Sebuabe and then Ewoyi. What you guys said is right. And you
Okay, sir.
chose Courage. I said what you said is wrong. Oh. Ewoyi and Theophilus, what they said is the right one. And the rest of you, I hope you had that. They chose to go by the general equation. That's fine. Or the overall equation. That's fine. I was thinking somebody will go by the very first one, where you add just a mole of water, but that's fine. That's right. Now, one thing they drew my attention to, which I don't think I mentioned, is that you need to indicate the states of the species. And in my equation, I think sometimes I indicate, other times I don't. That's bad. I didn't indicate, okay, I indicated this. I didn't indicate for water and this. But that's bad. You need to indicate the states. All of them, apart from water, the state is aqueous, AQ. All of them. Water is L, liquid. That's how you indicate the state. It's as simple as that. All of them, the state is AQ, aqueous. Apart from water, which is L for liquid, then you are fine. Remember I told you before that any species that is charged, that has a charge, whether it is plus or minus, the state is always aqueous. It's in the aqueous state, because it is only when you are put into water or you are in the aqueous state that you can reveal your ions. So it's important. Now the product, even though it's not a charged species, is in water because you added water. So the product is formed in water. So it has to be AQ. Take note of that. Then another thing is, you see the sign I have used all throughout. This equilibrium sign, you have to use it. This equilibrium sign, it shows that the reaction one is or can take place in both directions, and then equilibrium can be reached. What that means is that the reactants are combining to form the products. The products are equally combining to form back the reactants. So you take note of the sign that I have used, equilibrium sign. Half arrows. Those are half arrows. Okay. When we use the full arrows, 2 full arrows, it shows us that the reaction is reversible. And every reversible reaction eventually gets to equilibrium. A reaction must be reversible first and foremost before chemical equilibrium can be attained. So by use the equilibrium sign, the one I have used in all my equations. All right, let's move on. Now, the next thing I want us to look at is trend in acidity of hydrated cations. You see, these hydrated cations that we know them are acids. Okay, trend. You remember that word, trend. Trend. This one, trend. Trend like order. Okay, account for the trend. Account for the trend in atomic size across the period. You see, and down the group. Periodicity is where you come across this word a lot, trend. The hydrated cations, we can account for their trend, the trend in acidity. What that means is that, can we tell whether one hydrated cation is more acidic than the other? Yes, we can tell that. And that's what we want to look at. The first thing is that the greater the charge density of the central cation, the greater the pull of electrons towards itself away from the water molecules, and hence the weaker and more polarized the OH bond in water, leading to easier loss of proton. Some terms you need to understand. I need to explain charge density, polarized OH bond, and then easier loss of proton. Acidity is basically determined by how quickly H plus is released into solution. So if you have two substances, two acids, A and B, A is able to release H plus, that's a proton, H plus, easily, quickly, or quicker, or easier than B, then A is a stronger acid than B. That's how we measure strength of acids. It's about the ease with which H plus is released in solution. The easier you release H plus, the more acidic you are, or the stronger you are in terms of acid strength. And now that H plus can only be released easily when this bond, the bond that holds the H2O is weak. If that bond is weak, then it is easy for H plus to be broken away and be released faster or quickly in solution. So that's about acid and what the ease of release of proton means for the strength of the acid. The easier you release proton, the stronger you are as an acid. Now, charge density is defined as charge over size. The charge density of any ion is the charge of the ion divided by the size. Okay, take note of that, very important. So you can see that from the formula I've given you, if we're talking, this is not a chemical bonding, and a chemical bonding, we'll have talking a bit more about this. But just from that formula, you can see that the charge density is directly proportional to the charge. So the higher the charge density. And then it is inversely proportional to the size of the ion. So that the bigger the size of the ion, the smaller the charge density. Or the smaller the size of the ion, the bigger the charge density. So charge density will be greatest if you have an ion that has a very high charge, but at the same time, a very small size. Its charge density will be ridiculously great. Now, if the charge density is great, charge density basically, if you look at it, is just like how dense charges are on the central atom. Remember the central atom in the case of cation, in the case of hydrated cations, the central atom has water surrounding it. Okay, the central atom, like M. Remember M. Then you have a certain moles of water molecules surrounding it, coordinating it. So if the charge density on M is great, what will happen is that it will be able to pull electrons from the water molecules, and electrons will be pulled from the bond between the O and then the H. Water is OH, OHH. That's how water is. If the charge density of the central atom, the central cation is high, we'll be able to attract electrons. Remember, it's a cation. You attract the electrons in the bonds. When that happens, it weakens the bond. It weakens the bond. It becomes easy for the bond to break and for H plus to be released into solution. That substance, that hydrated cation, then becomes a strong acid. So take note of that. The greater the charge density of the central cation, the greater the pull of electrons towards itself, away from the water molecules, and hence the weaker and more polarized the OH bond in water, leading to easier loss of proton. The more polarized here only means that, as an English word, it becomes weaker. That's what it means. So this is one of the things that determines the acidity of hydrated cations. Charge density is 1. Now let's look at an example. Look at the example I have here. Okay, by the way, let me even say this. This only comes to play when you have the same molecules of water surrounding the cation. So in an examination, if it is the first principle they want you to use to rank the hydrated cations that are given to you, the molecules of water will always be the same. The molecules of water will always be the same. If the molecules of water are the same, the number of molecules of water are the same, then the charge density of the central atom or the cation is then what determines the strength of the acid. So you can see the order I've written here. Aluminium is greater than magnesium, and magnesium is also greater than sodium in terms of acidity. So aluminium with or hydrated aluminium cation is a stronger acid than hydrated magnesium cation, and it's also a stronger acid than sodium, hydrated sodium ion. Why? Because look at it. Aluminium has the greatest charge among the three: aluminium, magnesium, and sodium. It has the greatest charge, yet the smallest size. So you can imagine how its charge density will be ridiculously great. And that's how size decreases. Size decreases in that order. Increases in that order. Aluminium has the smallest size, followed by sodium, magnesium. Magnesium size is smaller. And then sodium has a bigger size. You know, these three elements are in the same period. Sodium comes first, followed by magnesium, then aluminium. And you know, atomic size decreases across the period. What it means that sodium that comes first is bigger in size than magnesium that comes second in that period. And then it's also bigger in size than aluminium that comes third. So aluminium has a smaller size than magnesium, yet it has a bigger charge than magnesium. Magnesium also has a smaller size than sodium, yet it has a bigger charge than sodium. It makes the charge density of aluminium greater than magnesium, and magnesium also greater than sodium. So because the charge density is great for aluminium, the pool of water molecules towards itself, or electrons from the water molecules towards itself, will be great. The OH bond becomes weaker, easy to break. H plus is easily released into solution, into water, and then it makes it a stronger acid. Okay, so that's another example. This one, all of them have the same charge, the same moles of water molecules. I told you that if you are to use charge density to arrange, the moles of water will be the same. The interesting thing about this one is that they all have the same charge of +1. It even makes it easy for you. So the one that has a bigger size will have a smaller charge density, and that one will be the weakest acid. You see that? So that's how come you see potassium, being last. The one that has the smallest size, like lithium, among the three, will have the biggest charge density. That one will have the strongest pool of the electrons in the OH bond. That eventually makes the bond weaker, H plus easily released. That one is a stronger acid. So lithium hydrated cation, lithium hydrated with X moles of water is a stronger acid than sodium and than potassium, because size increases in that order. These elements are in the same group in the periodic table, and down the group, atomic size increases. Now, the second criteria, if the cations are the same, the more hydrated it is, the greater its acidity. This is because the former can donate more protons than the latter. Okay, so if you are giving the cations, the hydrated cations, and they are the same, look at it, magnesium, magnesium. So they have the same charge, +2, +2. But what will make the difference will be moles of water. The moles of water for the first magnesium is 6, and the moles of water for the second magnesium is 4. They are all hydrated cations. Then you are asked to tell which one of them is a stronger acid, according to Bronsted-Lowry, than the other. And I'm telling you that the one that has more water molecules surrounding it is the stronger acid. The more hydrated the cation is, if they are the same, the one that is more hydrated, that is the one that has a greater acidity. Why? Because if you are more hydrated, it means you have more protons to donate. More protons to donate. More protons to donate. The more water molecules you have, the more protons you have to donate. It makes you a stronger acid. The strength of an acid is also determined, is also assessed by how much protons you donate. If you have more protons to donate, you are a stronger acid. That's what it means. Oh, okay. I don't have any example. That's all. Anybody has any question for me? On the strength of hydrated, of the acidity of, the trend in acidity of hydrated cations. I thought I have a question over there for us too, where you are asked to arrange, the following hydrated cations in increasing or decreasing order of acid strength, and give reasons. That's the part that makes you the correct chemistry student. Give reasons and explain. Your ability to make deductions, critical analysis, is what makes you the correct chemistry student. I don't have any example there, but let me give you one off head, and let's try. So you write these compounds I'm going to give you down. Mg H2O subscript 4, the charge is +2. Ca, that's calcium. H2O subscript 4, 4 moles of water. The charge is +2. And the third one, Be, that's beryllium. H2O subscript 4. That one to the charge is +2. Now analyze the three of them carefully and tell me, or arrange them in increasing order of Bronsted-Lowry acid strength, and give reasons for your order. Steven Matecho. Jasper Kuma.
Say,
Yes.
please, say BE into brackets H2O subscript 4 all into brackets charge of plus 2 followed by into one bracket Mg into another bracket H2O subscript 4 all having charge of plus 2, then Ca into bracket H2O subscript 4 all having a charge of plus 2.
Okay. Is that an increasing order of acid strength or is a decreasing order? Jasper, are you with me?
Say,
Yes,
please, can you hear me?
I can hear you.
That's the increasing order.
Okay, let me explain this to you. When you say increasing order, what you've just given me, when you say increasing order, then you are telling us that the last one that you gave, which is calcium, the one with calcium, is a stronger acid. Is that what you want to say? Because increasing order means the smallest one comes, then it increases. So the one at the end is the highest. The last one becomes the highest. Jasper, is that what you wanted to say? Oh, I think we lost Jasper. No, she's still there. All right, I hear you. How are you?
Say, the increasing order calcium into bracket H2O subscript 4 2 plus greater than Mg magnesium H2O.
No, hold on. If you use
4.
greater than sign, then you cannot be arranging in increasing order. If you use greater than sign, then you are arranging in decreasing order.
Okay, less than magnesium into bracket H2O subscript 4 with a charge of 2 plus, also less than beryllium into bracket 820 subscript 4, all with a charge of 2 plus.
Okay, so good. So in what you've just said right now, what it means is that you are saying calcium is a weaker acid than magnesium, and magnesium than beryllium. Is that what you wanted to say?
Yes, sir.
What are your reasons?
Say, you first told us that the greater the atomic size,
Yeah,
the lesser the lesser the acidity, or
the lesser the charge density.
lesser the charge density. Okay.
Yeah,
And then calcium is the highest over there in terms of atomic size.
that's true.
Its charge density will be the lowest.
Yeah, you're right.
Then
So
followed by
sure.
magnesium.
So because its charge density is the lowest, the pull that it will have on the electrons in the OH bond will not be that strong. So the OH bond will be stronger because electrons will not be withdrawn readily, making it difficult for the OH bond to break easily, for H plus to be released easily into solution. So it makes calcium a weaker acid. Beryllium is the one that has the smallest size, so it has the greatest charge density. The pull that it will have on the electrons in the OH bond will be the strongest, thereby making the OH bond weaker, easy to break, and H plus easily released into solution, and that determines strength of acid. So the beryllium one is a stronger acid. That's the explanation. Okay, so in explaining, you can say size, they have the same charge. All of them have the same charge. Size increases in the order BE less than mg less than Ca. That's increasing order of size. So because size increases in that order, charge density increases in the order, then calcium will come first, less than magnesium, less than beryllium. So you are saying beryllium has the highest charge density because it has the smallest size. Then you can conclude the higher the charge density, the stronger the pull of the electrons in the OH bond, the weaker the OH bond becomes, making it easy to break to release H plus. And that determines the strength of the acid, hence the order. That's all. That's how you explain these things. All right. So that actually brings us to the end of the Bronsted theory. But we'll come back and look at some of the differences between that theory and then other theories. But that's the end. The third acid classification based on bonding and structure includes as acids substances that do not contain hydrogen at all. This definition of acids was introduced in 1923 by the man J.N. Lewis, Gilbert Newton Lewis. Most of the time we just say Lewis, the American chemist whose name was given to the electron dot structures. There's something in chemical bonding we call electron dot structures, where we use dots or where we represent electrons as dots, in showing chemical bonding or how chemical bonding, whether it is covalent bonding mainly covalent bonding, actually, mainly covalent bonding happens between atoms. What electrons are shared and what electrons are left on each of the atoms we call the lone pair, or the lone pairs of electrons. Those electrons that are not involved in bonding, that are not used in bonding, are the ones we call the lone pairs of electrons. And we use dots, okay, to represent those electrons. That concept was the brainchild of J.N. Lewis. He brought about that concept. So it was named Lewis electron dot structures. Lewis electron dot structures. It's the same man over here. The name is Gilbert Newton Lewis. His theory about acids and bases was introduced or was brought, to the fore in the year 1923. Take note of that, very important. The Lewis definition is the most general theory, having no requirement for solubility of protons. So the Arrhenius theory is about solubility. You dissolve in water, produce H+, you're an acid. You dissolve in water, produce OH-, you are a base. The Bronsted concept is about protons. You donate a proton, you are an acid. You receive a proton, you are a base. The Arrhenius theory has none of those requirements. You don't need to be in solution to be an acid or a base. You don't need to have proton, hydrogen, to be described as an acid or a base. According to Lewis, an acid is a substance that can accept a pair of electrons to form what we call coordinate covalent bond. The key words here: accept a pair of electrons to form coordinate covalent bond. My question to you is, what is coordinate covalent bond? Kuma Jasper, are you there? Stephen, can you hear me? Seke, can you hear me? Seke Benoni. Yeah, Seke, you can hear me. What is coordinate covalent bond? Rejoice, Sedinam, can you hear me? Oh, some people have dropped. I don't know why. Jasper has dropped.
Sir, please, I can hear you.
All right, Sedinam, what is coordinate covalent bond?
It is a bond that shares electron between atoms.
That's all. How are you, Daniel?
Sir, a coordinate covalent bond is a type of covalent bond.
Yeah, excellent. 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 I like the way you started. It is a type of covalent bond. Yeah, that's how this question is answered. What is coordinate covalent bond? It is a type of covalent bond. All right. Finish it up.
So, in which two electrons come from the same atom.
I see. You didn't finish it well to my expectation. But that's fine. I just like the way you started. It's a type of covalent bond. By the way, what is covalent bond? Maybe we should start from there. Matecho Steven, what is covalent bonding or covalent bond? Steven, are you there? Jason Awaga. Courage Tenu. Well, can somebody hear me at all? Hello?
Hi.
Okay. Theophilus, what is a covalent bond?
Okay, covalent bond is a type of bond formed by sharing of electrons.
Yes. Covalent bond is a type of bond that is formed as a result of a sharing of electrons between the two atoms. All right. So what then is coordinate covalent bond? In coordinate covalent bond, the electrons that are shared between the two atoms is donated by only one. So Daniel, that's why you started nicely. You said it's a type of covalent bond. Once you mention that it's a type of covalent bond, you are making whoever is reading know that it involves sharing of electrons between two atoms. Only in that, then you add that part, only in that in this type, the electrons that are shared between the two atoms is brought forward by only one of the atoms. The second atom does not donate anything at all. So that's coordinate covalent bond. Now, there are two conditions necessary for coordinate covalent bond to be formed. One of them is that one of the atoms must have empty orbitals to accept the electrons. Then the other atom must have lone pairs of electrons to donate. And I explained lone pairs of electrons to you earlier as those pairs of electrons that are on the atom but are not involved in bonding. So one atom must have lone pairs of electrons to donate. The other atom must have empty orbitals to accept the lone pairs of electrons. Louis says that if you have pair of electrons, or if you accept pair of electrons, then you are the acid. And then if you can donate pair of electrons, then you are the base. So he says a Lewis base is a substance that can donate a pair of electrons to form coordinate covalent bond. The end result is that a bond is formed between the two atoms. That bond is what we call coordinate covalent bond. I want you to take note of the difference between Lewis definitions and Bronsted-Lowry. Acid, according to Bronsted-Lowry, is a donor. A donor. What is donating? Proton. But acid, according to Lewis, is an acceptor of something. What is accepting? Is electron pairs, not proton. So a Lewis acid is an electron pair acceptor, simply put, or is a substance that accepts pair of electrons to form coordinate covalent bond. A Lewis base is a substance that donates a pair of electrons to form coordinate covalent bond. Any question? Anybody has any question for me? We can't finish this concept. We'll continue later. In any case, a number of your colleagues have even dropped out of the class. I don't know why. So I'll pause over here. If anybody has any question, let the person asks. I think the network generally has become bad again. Even at my end here, I can see that. The 6 of you left. Anybody has any question? Some of them cannot even hear me. Oh, Jasper, you are back. Can you hear me? Matecho, Steven, can you hear me? All right. Let's end it here. We'll continue later. Have a good evening.